Welcome to today's lecture of the CBNST. In today's lecture, we will talk about errors in numerical methods. In the previous lecture, we had already seen that what is the basic definition of the error. Error is known as the difference between the true value and the approximated value of a measurement. So we need to minimize the errors in numerical methods to obtain best or perfect solutions. Before we minimize the errors, we must know what are the sources of the errors. So in numerical methods, there are three main sources of the errors. One is the input. The second is algorithmic, and the third is computational sources. So let's see what we mean by input sources. The input source is a source from where we are getting the input value of variables we need to measure. For example, let's say we need to calculate the area of a circle, which is, as we all know, which is pi r square. So if we get the input of the pi as 3.14 into r square, then you know that this is the not the actual value. This is only the approximated value of the pi. So here this introduces the input error into the formula, because the value we are inputting is in itself not exact and approximated. So such type of errors are known as input errors. Let's say the next is algorithmic errors. The algorithmic errors appears due to the steps involved into the algorithm. In many cases, we limit the number of steps into the algorithm. On the other hand, if we would have performed infinite infinite iterations into the algorithm, we would have achieved the perfect solution. But due to the limitations, we always limit the number of steps into the algorithm. For example, we had lots of series. Let's say if we have a series 1 plus x square plus and so on. So what we used to do, depending upon our precision, we used to ignore the higher terms of the series. And hence, we approximate it to few major terms. So this is called as limiting the number of steps from infinite number of steps to a finite number of steps. Due to this, the error will introduce into the final computation, and such type of introduced errors are known as algorithmic errors. Now, the last source of the error is the computational source. As we all know, the devices, the calculating devices, the computers have limited resources, storage spaces. So depending upon those storage spaces, the computer round off the numbers. As we know that the computers have 8-bit registers, 16-bit registers, 32-bit registers, and today they are larger enough, but still they have limitations. So they limit their computational observation depending upon the storage capacity. In that case, whenever they store a smaller sized data, let's say 3.14289667, instead 3.128967398245. So this should have been stored, but due to the limitation of the storage capacity, it stores only this information. So this will introduce the computational errors in further computations. So these are the three main sources of the input errors, sources of the errors: input, algorithmic, and computational sources. Now let's talk about the types of the errors. What are the major types of the errors that we can discuss here for the numerical analysis? One is the inherent errors. So inherent errors which occur due to the limitation of the, let's say, experimental device. If you want to measure a length, let's say if you want to measure length of this straight line, we need to use some instrument. Let's say we will be using a ruler, we will be using a scale. that has limitation to measure this till centimeters, but it will not be able to measure this in millimeters. So just because of that limitations of the instrument, we will be able to measure this to the precision of centimeters only, and we will not be able to measure this in millimeters. So just because of this, the inherent errors will occur, and such type of errors will called inherent errors, and this error will continue in further computations. So this is called inherent errors. Next is the rounding errors. In the previous lecture, we had seen how we can round off the numbers. We had seen that a 4-digit number, let's say 31456 can be rounded off till this 3.1457. So we have seen this rounding off of the numbers, which is required due to the limited storage, due to the computational limitations, and this rounding always introduces errors and will not be able to achieve the perfect answer. So such type of errors introduced in computations are called as rounding errors. Next is the truncation errors. Right, truncation errors can be related with the algorithmic errors, where we used to truncate the number of steps. Like I have already seen in any series, let's say if it is 1 plus x square plus x cube plus and so on. We had already seen this in the algorithmic sources. So whenever we truncate this series in our calculation to this much only, or to any specific desired result, to any specific desired number of terms, the error introduced in this will be known as truncated errors. So whenever we don't keep all the terms and we truncate this series to some specific number of terms, the error introduced into the computation will be known as the truncation errors. So these are the three top errors. Now let's talk about the other three errors which we will be using in the calculation also, in numerical sums also. So one is the absolute error. So the formula for the absolute error is written here, that the difference between the true value and the approximate value is known as the absolute error. So if we say that the absolute error is equal to absolute value of x true value minus the experimented value. So you can see this is the absolute difference between the true value and the experimented value, where this xt represents true value and xe represents the experimented or approximated value. Let's say in any calculation, if we have the true value of this pi, let's say 3.14579, and the approximated value of the same variable is, let's say, 3.14, then the absolute difference between this can be 0.00579. So this will be the absolute error in the calculation. Next is the relative error. Obviously, relative error means whenever we measure the error in reference to some value. So here the relative error, which is represented by ER, is equal to the absolute error. This is absolute error divided by original value, that is xt. We can also write this in this way. We will take this absolute error, divide it with the original value. This will be known as the relative error. So in the same example, if you would like to find out the relative error, so this will be 0.00579 whole divided by the actual value, that is 3.14579. So this is the relative error. This way we can obtain the relative error of any computation. And in the last, that is the sixth, which is known as the percentage error. So we need to represent the error in the form of percentage. Just to obtain that, we simply need to multiply this relative error with 100 and we will be getting the percentage error. So let me show you the formula for the percentage error, which can be written in many ways. So let me write this percentage error. This is EP, can be written as, let's say, xt minus xe whole divided by xt. This is the representation of the relative error multiplied by 100. So this will give you the percentage error. This can also be written in this way. Let's say E of R, that represents the relative error, multiplied by 100. So in this way we can obtain our percentage error. So these are all the types of errors, and I hope you have understood the sources of errors and types of error. It is important to understand the errors because we need to minimize these errors to get a perfect result and the best result in our numerical methods with our numerical techniques. So that's it for the lecture. We will meet in next lecture and we'll discuss some more topics of the numerical method.